Good morning, students. A very good morning to one and all. I am happily welcome you all for this gate preparation session. We have already discussed about the basics of pipelining in the last session. So with no further delay, we will move on to the next advanced concepts, which are all related to the um, gate related computer architecture oriented questions. So myself R.Narendran, I am going to have the session of gate. So today we are going to have the session titled Pipeline and Memory or Data Accessing Techniques. So in pipelining, there are different kinds of problems which have been asked so far in GATE forum. So out of which numerical problems, we can differentiate pipeline related problems in architecture as numerical and non-numerical problems, that is logical problems. So today we are going to have the problems which are related to numerical concepts. So let us have the look at the first concept. Okay, so this is the first question. Here goes. So I am reading out the question so that you can able to understand it much better. So first question, consider the following processors. Okay, ns stands for nanoseconds. In this, in the question itself, they will be giving the proper explanations regarding the short forms. Okay, so assume that the pipeline registers have zero latency. Okay, we have discussed about latency and CPI, cycles per instruction set, related formulas in the previous session itself. Just go through that session so that you will be clear with what are all the basic concepts we are in need of in solving numerical related computer architecture gate questions. Okay, so here they have given P1, P2, P3 and P4 are the four processes. So P1, what are the things they have given means 4-stage pipeline with the stage latencies 1 nanosecond, 2 nanosecond, 2 nanosecond and 1 nanosecond. So coming to the P2, that is processor 2, they have given 4 stages of pipeline with a stage latency as 1 nanosecond, 1.5 followed by 1.5 and finally 1.5 nanosecond. So P3 is the third processor which gives pipeline stage latency as 0.5, 1, 1, 0.6 nanosecond and finally 1 nanosecond. Okay, it's a 5-stage pipeline latency. So followed by P4, that is processor 4, which is also having 5-stage pipeline latency, 0.5, 0.5, 1, 1 and 1.1 nanoseconds. So what they have asking means which processor has the highest peak clock frequency. Okay, the options are given as A P1, B as P2, C as P3 and D as of course P4. So this is the question they have given. So out of which we have to find out which processor is having the high peak clock frequency. So let us have a look at the basic explanations which are related to this pipeline related problem which is given. So it's very simple. So what is given? They have given there are 4 processes and they have given also the stage latencies, pipeline latencies at each stages. So here they have out of 4 processors, first two are having 4-stage pipeline with latencies, and next two are having 5-stage pipeline with latencies. So it's very simple. We have already discussed these kind of formulas. So let us have a look at this. So the solution, here it goes. So clock period, CP in short form, is a computation between maximum stage delay in addition with overhead. Okay, so for each and every processors, we are going to calculate clock period. Okay, so here so CP1, okay, that is CP of P1, which implies clock period of processor 1. It's a maximum of 1, 2, 2 and 1. Okay, so in the we have already seen about these kind of things, which is already given in the question itself. So we are just substituting the values in those particular concepts. That's it. So we are calculating the maximum latency out of 4 pipeline stages. So which is found out as 2 nanoseconds for CP1 and 1.5 nanosecond for CP2, and similarly when we are calculating the maximum value out of latencies for P3, we are getting 1 nanosecond, and similarly finally we are having 1.1 nanosecond in with respect to P4. So in this we already know that frequency, that is frequency is what they have given. Frequency is inversely proportional. Yeah, right. So inversely proportional to clock period. So least clock period will be having the highest clock peak frequency, right? So which processor is having the least clock period, which will be having the highest peak clock frequency. So based upon this concept, we can find out the frequency as f of P3 is equal to 1 by 1 nanosecond. So out of this we are having first one 2, second one 1.5, and the third one 1 nanosecond, and fourth one is having 1.1 nanosecond. So out of this 1.1 and 1, so that is 1.0. So we are in these kind of numerical problem related questions, so we should concentrate on the floating point also. Okay, so maybe it may be 0 point something values also. So that value itself decides the options, that is your answers. So just take it in mind that you should have a good look at what are all the data which is precisely given in the concept. So by substituting that value, we will be getting 1 gigahertz. So the frequency is 1 gigahertz for processor 3. So here is the answer. So from that itself we will be getting the answer. Okay, so processor 3. So moving on to the second question. Okay, this is quite interesting question. So I am reading out the question so that you will be getting understand about the concept. So host A sends a UDP datagram containing 8880, okay, 8880 bytes of user data to host B. We are having host A and host B. Okay, so host A is sending data to host B. That is the given thing first. So Ethernet frame. So okay, we are having a UDP, user datagram protocol. Okay, so there are two types of transmission protocol, TCP and UDP in common. So out of which UDP is a wireless protocol. So what are the things given? Ethernet frame may carry data up to 1500 bytes. Okay, that is MTU, which we can represent it as MTU. MTU is equal to 1500 bytes. So the size of UDP head, okay, the size of UDP head is, we will be having the UDP IP head, right? So so the size of that head part is 8 bytes. Okay, so and the size of the IP head is 20 bytes. Okay, so UDP head and IP head. Okay, so in the frame format we will be having a head and tail. Okay, so in this you are having 20 bytes. There is no option field in IP header how much total number of IP fragments will be transmitted, and what will be the content of the offset field in the last fragment. So the question is very pointed question. These kind of questions will be saying. So we have to analyze. So before analyzing this, we should have a basic knowledge about what are all the UDP head, IP head, and what are all the different types of bytes which are there in the UDP and TCP protocols. So the options given are 6 and 95, 6 and 7400 bytes, and 7 and 1110 bytes, and 7 and 8880 bytes. Okay, so the question is very simple and very diplomatically they have asked. So they have given user datagram data in terms of bytes 8880, and they have also mentioned the MTU as, they have given MTU as 1500 bytes. Okay, so 1500 bytes they have given. So also they have given the header data. So head data and respective IP head data also. So we have to find out the offset value and total number of IP fragment segments. So this is the thing they have asked. So by means of this diagram itself, we can able to analyze the offset and bytes. So so in the diagram itself, I have given total number of bytes as 8880, and the MTU is 1500. These two things are already been given in the basic concepts of the program. So that is the given data. So we have to find out the offset. Okay, so we are splitting this data into 0 to at most 1500. Okay, so that is 0 to 1471. Okay, so we are splitting the data into 20, 20, 20, 20 and 20 followed by 20. So why we are splitting the data for 20 means they have given the IP header as 20. Okay, so for the first segment only we are having 28. So this 28 segment is concerned with the IP header of UDP. Okay, UDP head. So followed by the other things are under the IP header. Okay, so IP header has 20 bytes. Okay, so based upon this incrementation of 20 20 20, so we'll be having the value, right? So 0 to 7, so the offset value finally we are calculating as 8872. That is the final value we are obtaining. So here I am marking that. So 8872 divided by 8. So we are getting the value as 1109, which is approximately equal to 1110, right? So which is approximately 1 or 2 bytes we can match up with the given data. Okay, so we are having the data as 695, 6 7400, so 7 1110 and 7 8880. So out of which the apt answer is 7 and 1110. So the right option is option C. So moving on to the next interesting question. So this question is quite interesting, which is related to the how the data is accessed. Okay, so we are having the data accessing parts, right? So how the particular data can be accessed, so that's the key thing behind these kind of questions. So consider the following program segment. Here R1, R2, R3 are the general purpose registers. We already know. So we are in general we are mentioning the GPR, that is general purpose register, as R1, R2, R3 up to etc. Rn, right? So that is the given data. So we have to analyze the instruction operation and instruction size in terms of words they have given. So let us see what are they given. So move R1 comma 3000, content of 3000. Okay, so that is the basic operation is the content of 3000 location will be moved to R1. So next one. So next one, R2 comma content of R3, that is the memory location R3's content will be moved to register 2, that is the general purpose register R2. So we have to mark this looping statement. These are all the key things they will be giving. Okay, so based upon this criteria, we are clearly having the idea that this is a looping condition. So it will be iterating n number of times. Okay, so that n number of times, how much time it is looping, that plays a very important thing. So how much we have to be clear with that. Okay, so let us see what are the other things given. So add R2 comma R1. These are all simple. We are adding the content of R1 and R2. And placing the result in the R2. So next one, moving the R2 content to, so R2 value to the content of R3. So next we are incrementing the R3 and decrementing the R1, and when the branch is not 0, then the loop will be there. Okay, so that is they have given. So next finally we will be halting the program. Okay, so simultaneously you have to be clear with what are all the instruction sizes they have given. Okay, so how much size the instruction is carried out, that is also very important. So they have clearly mentioned in terms of words. So total number of words is the instruction size criteria they have given. So we are very clear with the data which is given. Okay, so we have already seen about mnemonics and what are all the meaning of move, add, increment, decrement, bn is that is a branch not taken, and that is branch not 0. So halt and these kind of conditions we are very familiar with. So we have already have a look at these kind of basic criterias in the previous session itself. So what is the task they are giving? So what is the task they are asking us to find out? That is the remaining part of the question. So assume that the content of memory location 3000 is 10. So the content of memory location here they have given the content is 10. So and the content of register R3 is 2000. So the content of register R3 here they have given, right? So this is 2000. Okay, so content is 2000. The content of each of the memory location from 2000 to 2010, okay, is 100. Okay, so 2000 to 2010 is 100. So, and the program is loaded from the memory location 1000. So the program is loaded, this the whole program, we are seeing this whole program, it is the content is loaded from the location 1000. From 1000 it is moving. So all the numbers are in decimal. Assume that the memory is word addressable. So yes, the memory is word addressable, right? So because they are mentioning the instruction size as number of words. So the number of memory references for accessing the data in executing the program completely is. So here is the main question. For this question only they have given this much of data. Okay, so finally what they are asking, the total number of memory references for accessing the data while executing this program. So in simple we can say they are asking for total number of memory accesses for memory reference. So here is the solution which is provided. So first memory reference R1, that is R1 implies M of 3000, right? So and this loop which runs for 10 times. Okay, why? Because the content of memory location of 3000 is 10. It is already mentioned. So the content of memory location 3000 is already mentioned, right? So here I have also written that. So 10 is given in the question itself, they have given. So the loop will goes for 10 times. So R2, that is the memory location of R3 is moved to R2, and the content of R2 is moved to the memory location of R3. This will be running 10 times as it is in the loop. Okay, question is very simple. So there are two memory references every iteration, right? So there are two memory references. This itself also they have given. So how much memory references they are having? So 10 into 2 is equal to 20. So extra 1. So the final answer is correct answer is 21. So when they are asking for options which are related to 21, then it is the right answer. Okay, these are all the basic what you can say numerical computer architecture program. In general I want to say that numerical architecture, so in computer architecture concept, numerical problems plays a very important role. These problems are very simple and easy to analyze, so it will be better to understand. So for example, in this question itself I am having a clear cut idea, right? So here in this question they have given so much of data. So in this question increment of R3, decrement of R2, so R1, looping of branch not taken, these things are not necessary, right? So these things are that much not effective and necessary for solving this question. So it's a kind of trickiness they are handling. So while suppose when you are having a question visually, when you are seeing these questions, these type of questions, don't become panic. Okay, so the basic thing is the question may be very simple. Within 2 to 3 lines itself, the question may be given, but the data will be very high. The data which you want to analyze is will be very high. But on the other hand, like these questions, so when the data is when the question size and data are very large when it is given, so the basic thing is there will be only few data that is very useful to us. So based upon picking up of questions like this, you have to be clear with these kind of essential data. You have to segregate essential and non-essential data while handling or solving these kind of problems. So that's the important thing you have to learn from these kind of questions. So So numerical questions are very important in these kind of gate questions. So moving on to the next part. So this is quite easier, I think so. So assume an L1 catch. So we are now moving on to the part of catch memory. So L1 catch. So we are before I want to give you the clear cut idea about what are all the catch memory and its types. So we already discussed in the previous sessions regarding catch memory. So just I want to give a brief gist of that. So cache memory is the fastest memory and it is very useful for frequent access of data. So like cookies and and these kind of lightweight datas, the cache memory will be handling. So and this is the very fastest memory out of the different kinds of memories available in the field of memory devices. So and in the field of computer architecture also. So L1, L2, L3. So these are all the three different types of cache memories. So out of which L1 is the first primary cache memory. Okay, so this is the primary cache memory. So L2 is the secondary cache memory and L3 is the tertiary cache memory. So when I am going to search for a data, so the computer will search for that particular data. That is in search of means I am requesting a particular data to the computer. So in that time, the computer will search for the data in the cache memory. So we are having different types of cache memory, right? So cache memory slots. So out of which the computer will be asking the particular requested data in the L1 cache first. So when it is there in the L1 cache, so it will be directly given to the main memory so that it can able to process the request. So suppose when there is a data miss, that is when we are unable to get the data from the L1 cache, then the L1 cache will shift the request to the L2 cache. So then the computer will search for data in the L2 cache memory. So also when there is a availability of data, then it will be returned to the main memory. Okay, so suppose when there is a data deficiency or data inconsistency that prevails in the L2 cache also, so in that case it will be moved on to the L3 cache. That is the request of particular data search will be moved on to the L3 cache. So this L3 cache is the tertiary cache, so which will be handling the remaining part of the search. So suppose when there is a data available in the L3 cache, then it will be returned to the main memory. So this is the basic idea about cache memory. So these are all the cache slots. Okay. So next part. So we are now familiar with the revision of cache memory and its types. So next we will be move on to the revision of cache hit and cache miss. Okay. So hit. Okay, so catch hit and catch miss. So I have already told you that when you are in search of a particular data, the computer will ask for the particular requesting data into the cache memory. It may be in L1 or L2 or L3. So whatever type of cache memory it will be asking, that's not a matter. So when it is searching for a data and the data is present, which may be in L1 or L2 or L3. So when the data is present, so it is considered as hit. That is, the data is accessed. So suppose when the data is not accessed or data deficiency occurs or data inconsistency occurs, so then it is considered as a cache miss. Okay, so these are all the basic things regarding cache performances. So now moving on to the question. Okay, so assume an L1 cache with a hit rate. Okay, they are mentioning it as hit rate. So the rate at which the process of data is accessed. So when it takes 10 seconds to reach particular data, then the hit rate is 10 seconds. Okay, so likewise miss rate also. When there is a data not available in the particular cache memory, then it is considered as miss. And when we want to move that particular searching or missing data into that particular location, means the time taken to move a particular searching data to the cache memory is called as miss rate. Okay, so these are all the things they have given. So assume that L1 catch with a hit rate of 70% and L2 catch with a hit rate of, sorry, with a local miss rate of 10%. If there are 1000 memory accesses, consider this is very important. So they are mentioning it as 1000 memory access initially by the CPU. Then the number of access that will find a hit in the L2 catch. So in the question itself, they have given there are two types of cache memory they are dealing with, L1 and L2, not L3. So we will be having L1 and L2. So there is a miss occur in the L1. So we are going on to the search of data in the L2. So the question they have asked is here. So the number of access that will be find a hit in L2 caches. So we have to find out. So they have given option as 270, 320, 480 and 620. So here is the explanation and the solution for this question. So number of access that will be that will find a hit in L2 cache is equal to miss rate of L1 is manipulated with hit rate of L2. The total divided by total number of memory accesses. So this total number of memory access they have already given. So 1000, right? The question itself they have given. So also the miss rate and hit rate of L1 and L2 are also given. So everything is given in the question itself. When these kind of questions are asked in a get forum, then you are very lucky to have these kind of questions. So you can easily do and predict the answer within a fraction of a second whenever you are seeing these kind of questions. So only thing is you have to practice. So the practice when you are very familiar with these kind of formulas and manipulating of data related numerical problem related computer architecture problem solving, then you will easily crack these kind of questions within a fraction of a second. You know, I also tell you that these kind of questions are very simple, and when you are seeing these kind of questions, attend these questions first. So it is a not a time consuming problem, it is a time efficient problem. So just we are substituting 30% into 10,000 instruction, sorry, 1000 instruction plus 90% into 1000 instructions divided by total of 1000 memory accesses. Okay, so when we are computing, we will be getting the answer as 270. So the right option is 270, that is option A. Okay, so the next question, it's also related to the catch. So that is memory access. Okay, so I am reading out the question, just be concentrate on the syllables. So a catch has a hit rate of 95% and the hit time is 10 seconds, that is 10 nanoseconds. The catch block size is 32 bytes and the word length of the processor is 16 bits. Okay, they have given hit rate, hit time, total number of memory block size 32 and word length is 16. Okay, so these are all the given data. So during a catch miss, it takes x number of nanoseconds to fetch the first word of block and 5 nanoseconds for fetching each subsequent words. So it takes x amount of, suppose you are considering as a variable x. So okay, that we will be having to find out. Okay, so x nanoseconds to fetch the instruction and 5 nanoseconds to fetch the subsequent instruction. So the average memory access time is 15 nanoseconds. Okay, so memory access time. So average memory access time they have given AMAT, average memory access time is 15 nanoseconds. Okay, likewise they have given hit rate. Hit rate is equal to 95%. Similarly, hit time. Okay, so hit time is equal to 10 nanoseconds. Okay, word length is equal to 16 bits. Okay, word length is 16 bits. Okay, so these are all the data given. So you have to find out the value of x. Okay, so what's the value of x? Suppose that I am searching for a data, that is the data is missed in the particular location. So how much amount of time in terms of nanoseconds I am going to fetch the first word? So that is the value of x. So quickly we will move on to the solution part. So we already know that AMAT, average memory access time, is equal to hit time of L1 plus miss rate of L1 into miss penalty of L1. So we know that miss penalty of L1 is the time taken to fetch the particular memory block into the from the particular memory. Okay, so that is miss penalty. So so here the solution goes. Number of words in the block is already given as 32 by 2 is equal to 16. It is already given in the question itself. So we are converting that particular data into bytes. So for that only we are having. So 32 divided by 2 is equal to 16 words, as each word is 2 bytes, right? So a time to fetch the particular memory block from the memory is equal to first word into x nanoseconds. So that is very important. This is the part of the question we are going to find out. Okay, so plus 15 into 5. Okay, these things are given in the question itself. So we already know that average memory access time, AMAT, is average memory access time, is equal to 15 nanoseconds. So 15 is equal to 10 plus 0.05 into miss penalty of L1. By substituting the value, we can be able to get 10 plus 0.05 into x plus 75. So the final answer is 25 nanoseconds. Okay, so the option C is the right answer. Okay, so that is the given data. Okay, so finally, just a simple question for a quick breakthrough. Okay, so it's a concept related to memory blocks and accessing of particular data. Okay, that is the given thing I have given. So let us move on to the question. Consider a direct mapped cache with 64 blocks and a block size is 16 bytes. Okay, to what block number does the byte address 1206 map to? Okay, so the question data is very precise, very simple. Consider a directed mapped cache. Direct mapped cache. There are two types of cache mapping, direct mapping and indirect mapping. So out of which they have given direct mapping. So direct mapped cache size is 64 blocks and block size is 16 bytes. To what block number the address 1206 will map? That is the question. Okay, so here is the answer. The block size is 16 bytes. Memory block number is equal to byte address divided by block size. So it is equal to 1206 divided by 16 is equal to 75.3. Okay, it's a pure computation. You should be clear with the basic formulas in the sense how to compute the block number of the memory and block number of the cache. Okay, so the given byte address, that is 1206, is a part of 75th block. Okay, so we have computed memory block size is equal to byte address by divided by block size. So by substituting here we have got 75.3. So the approximate value is 75. So it can be in the 75th block. Okay, so we have computed the block size, sorry, the block number. So we are substituting here. So we have what we have find out 75 block, 75th block. So we are substituting here. So catch block number is equal to memory block number modulus of so that is modulo division of number of blocks in catch, that is 75 modulus of 16. We are getting the answer as 11. Okay, so 11 is the right answer. So the option C. So option C is the right answer. Okay, so today in this session we have came across different types of problems, gate related questions. Okay, I think you will be very clear with the concept of numerical problems, how they will be asking, how we have to cope up with these kind of things. For the past few sessions, we are dealing with um, uh, pipeline related architectural problems, followed by memory related problems, and how to access a data. These kind of things are we are concentrating. Okay, so we have to very clear with the basic formulas. So just have a quick overview. Okay, the first question we have seen about the problem of finding the clock frequency. Okay, so the clock frequency we have find out. So the next question we have find out the um, offset value and the total number of IP fragments. So next we have find out memory reference accessing memory reference, total number of memory references for accessing a particular data. So followed by a quick recall of catch memory related problems: hit rate, miss rate, catch hit, average memory access time, and uh, total number of time required or blocks required for fetching a particular data. So finally we have came across finding out the block number to which a particular address is mapped to. Okay, so these kind of questions are very common in gate while solving gate questions. Okay, I think this session will be very interesting for you. Hope you will work out these kind of problems. In the net itself, you can find out so much of problems related to numerical computer architecture oriented gate questions. So just have a basic look at the different kinds of numerical problems in computer architecture, so that you will be able to solve and crack these kind of questions very easily. Okay, with that note, I thank you very much for all of you for kindly listening to these kind of questions, and for patiently listening to this session. Okay, once again I am thanking you all for patiently listening to this gate session. Thank you very much.